In this video, we're going to see what happens when we mix together the Pythagorean theorem and the trig functions that we know and love. So consider this angle here that has a radian measure of theta. A circle with a radius that is r units long is centered at the vertex of the angle, and then the terminal point is x units to the right and y units above the center of the circle. So we see a right triangle in this diagram. So the hypotenuse is that segment from the origin, or the center of the circle, to the terminal point. We have a horizontal side length here with a length of x, and a vertical side that has a length of y units. And the hypotenuse of this triangle is r units long because the radius of the circle is r units long. So you should see that the radius right there is the same as the hypotenuse. So the Pythagorean theorem then tells us that x squared, so x is going to be the length of that horizontal side, x squared plus y squared is equal to r squared. But the trigonometry that we've covered before tells us that x is equal to r times cosine of theta, and y is equal to r times sine of theta. And therefore, if we take this equation here, we plug in those outputs of the trig functions, we end up with r times cosine of theta squared plus r times sine of theta squared is equal to r squared. And if we distribute that exponent of 2 in both of these terms there, we end up with r squared times cosine of theta squared plus r squared times sine of theta squared is equal to r squared. And we could actually divide both sides by r squared. We could factor out an r squared from the left-hand side, and then divide both sides by r squared, and we end up with just cosine of theta squared plus sine of theta squared is equal to 1. So if we do a little algebra there, we end up with this equation right here. Let's look at this in a similar context, but this time, let's just say that the radius of the circle is 1. Or more specifically, if we draw in this right triangle, we'll say that the hypotenuse has a length of 1 when measured in hypotenuse length. So the hypotenuse is, of course, 1 hypotenuse length long. And therefore, we'll say that x represents the length of this horizontal side measured in hypotenuse lengths, and then y represents the measure of that vertical side in hypotenuse lengths. So we'll say we have a hypotenuse of 1 hypotenuse length, and then the terminal point is x hypotenuse lengths to the right and y hypotenuse lengths above the center of the circle. In which case, we have x squared plus y squared is equal to 1 squared, and 1 squared is just equal to 1. But in this case, x is equal to cosine of theta, y is equal to sine of theta. And so if we plug those in, we end up with cosine of theta squared plus sine of theta squared is equal to 1 squared. And 1 squared is just equal to 1, so I'm just going to erase the exponent of 2. So based on what we know about trigonometry and the Pythagorean theorem, we end up with this equation, which ends up being pretty important. This is what we call the Pythagorean identity. It's just a mixture of the Pythagorean theorem and using cosine and sine and the way we know how to use them. So let's make one quick note about notation. So in math, we tend to try to be as efficient as possible with our notation, but sometimes this ends up being a little confusing at first. So when we write sine of theta squared, this is how we should feel comfortable writing this. This really kind of expresses what we want to express. But you see we have kind of a lot of parentheses there. So mathematicians decided it'd be nice if we could omit some of those parentheses to speed up our writing. So sometimes we end up writing sine squared of theta, so we move the exponent of 2 over to the sine function, and then put the input over here. So these two things mean the same thing. So if you see the exponent of 2 moved over to the sine function, that just really means sine of theta squared. We could even be more efficient, and it's sometimes common to see with trig functions that we just omit the parentheses indicating the inputs. So we could write sine squared of theta and just put no parentheses there. This is kind of a common thing to do, although it's kind of confusing. So if you see something like this, it's good to think of this in terms of sine of theta, and then that whole thing squared. So if you see something confusing like this, just rewrite it in a way that makes sense. So we saw that the Pythagorean identity looked like cosine of theta squared plus sine of theta squared equals 1. It's common to rewrite this and write it as cosine squared of theta plus sine squared of theta equals 1. Sometimes we omit the input parentheses and just write cosine squared theta plus sine squared theta is equal to 1. All of these things are saying the same thing. This one is maybe the most precise, but it has a lot of parentheses, which you might consider extra baggage. So it's common to see them written in a form like this that's just a little shorter and easier to write.